Right, so this vector has an initial point and a terminal point. And if I were to state the initial and the terminal points in terms of coordinates, right? So suppose this is the point, A is, I don't know, 5, 7, okay? And suppose B is 7, 13, okay? To go from A to B, right? I know I need to go, over horizontally a little bit and vertically a little bit, right? So to go from A to B, how much do I go horizontally from A to B? A distance of 2, and I have to go 2 to the right, correct? Now, how can I do that? It's 7 minus 5, that would give me that 2, right? And how much would I go vertically? 6, right? And that would be 13 minus 7. That would give me a positive 6. So you see how order matters? Because if you did 7 minus 13, you would go down 6 units and go to the completely different place. So that means I can write AB, okay, vector AB. I can represent it, and in terms of, how to go from A to B, sort of like a little recipe, right? So I can say you go positive 2 a little bit in the horizontal direction and positive 6 in the vertical direction, right? And if I put it in these, I don't know what kind of brackets they are. Those aren't curly brackets. Huh? Yeah. Yes. Okay. So if I put it in that form, then that represents vector AB. And we call this component form, because you remember from yesterday, this is the x component and the y component. So this is the component form of this vector. So what did we do to come up with the component form? We didn't even have to draw it. If we just had A and B in coordinates, all you have to do is x2 minus x1 and y2 minus y1, and that's your component form of the vector, okay? Often, in general form, the component form is written as A comma B, like this, okay? So take a look. Find the component form of AB with initial point this and terminal point that. So we say AB is equal to, okay? So in the first case, we're going to do 1 minus 1, x2 minus x1, 3 minus negative 3. So AB is 0, 6. Okay, do you have to show me this arithmetic step? No, I know you guys can add and subtract, right? So let's see if this works. So the initial point here is 1, negative 3. This is point A. So this vector form is telling me how much am I supposed to go horizontally? How many units? 0, so nothing. And then I need to go 6 units up vertically, right? So if I go up 6 units, what point is that? 1, 3. Oh, hey, that really is the coordinate of B. So that was a pretty good, recipe for creating, vector AB. Okay? All right. Now, how about the magnitude of a vector? So if all you're given is A and B, right? If all you're given is this point and this point, well, are you able to find the distance of vector V, the magnitude of vector V using the distance formula? Yeah, of course you can find the distance form. You can use it, the distance formula. Well, what is the distance formula? It's this. x2 minus x1 squared plus y2 minus y1 squared, right? But what did we just say x2 minus x1 was? It's that A component, right? And what did we just say y2 minus y1 was? That B component. So another way of writing this formula is, hey, you know what? It's if you have the component form of the vector, you could just do the square root of A squared plus B squared. Okay? So find the magnitude of AB with initial point A and B. So this is the same vector as above, right? In component form, AB is 0, 6. Magnitude of AB then is the square root of 0 squared plus 6 squared, which is just 6. Okay? And does that make sense? Does this have a magnitude of 6? Yes, it does. Okay? Okay. So just like matrices, vectors in component form have their own way of adding and subtracting. If you have a vector in component form, the way in which you add them, basically you just add the first components and you put them here, and then you add the second component and you put them here. What does that remind you of? What is that like? Adding and subtracting what? Matrices, right? It's exactly the same, okay? All right, so take a look here. And then, scalar multiplication is the exact same thing, okay? So take a look here. You have WYZ, huh? So scalar multiplication, you would just distribute the k to each of the variables, to each of the components. We're actually going to do it here, like the 2y and then minus 4z. So if you have 2w. If you have 2 times w, this is 2 times 2 negative 5 plus 1w, 2 comma 0, minus 4 times negative 1, negative 4. So what happens here is you distribute the 2, 4, negative 10, plus 2, 0. And then here it's minus if you distribute the 4. And it's up to you if you want to do plus and then distribute the negative as well. It's the same. So negative 4, negative 16. Okay. So to add these, basically all you're going to do is you're going to add the the x components of each of them. So 4 plus 2 plus 4, that's 10, comma, the y components, negative 10, 0, positive 16, that's 6. Okay? We're cool? Yeah.
Can we go over that one more time? That second to last step.
This one?
Yeah.
So we just distributed the scalar. So 2 times the spectrum means 2 times 2 and 2 times negative 5. So it's 4 and negative 10. Mm-hmm. And then here there's nothing to do. And then here I distributed the 4. So it's 4 times negative 1, 4 times negative 4. Mm-hmm. And then here we just add the first component. 4 plus 2 plus 4.
Oh,
that's 10. Okay. Mm-hmm.
Just to make sure, you could do negative 4 times everything and then just make it a plus, right?
Okay. All right. Now let's talk about a unit vector. So remember how vectors can represent physical quantities, right? Like a speed or a whatever, a velocity and so on. So, but sometimes you might not need, a 54 unit vector. Sometimes maybe all you need is a direction of a vector. In that case, you can just have a unit vector. A unit vector is a vector with a magnitude of 1. Okay? So, take a look at this vector v here. Okay? That vector has a length of 2.5. It has a magnitude of 2.5. Its unit vector u is this tiny little vector. And do you see how it has exactly the same direction as v, but it's only 1 unit long? Okay? So if I were to take vector v of 2.5 units, what should I do to it in order to make the magnitude equal a 1? What am I supposed to do? You can divide by its magnitude, right? If you divide it by 2.5, you get a magnitude of 1. In fact, that is all you do to find a unit vector. Okay? You just divide v by its magnitude. In fact, so here actually these all need little arrows. Okay? So U is vector V divided by the magnitude of itself. Yes.
So it only ever has the brackets rather than the magnitude?
The vertical bars, you mean? Correct. Okay? The magnitude is always 1. Okay? Yeah. Okay. So find the vector U with the same direction as this. Okay? So, 4 comma negative 2, that's a vector that, you create by going 4 horizontally and 2 vertically, right? You want to find the unit vector. Now, the magnitude of this, right? Let's see what the magnitude of that is. So, V magnitude is, well, that's the square root of 4 squared plus negative 2 squared. That's root 20, right? So, magnitude is 2 root 5. Correct? Now, unit vector unit vector U is going to be V over magnitude of V. So that's going to be, okay, what's vector V? 4 comma negative 2 over what? 2 root 5. Okay, U is, okay, so this is just like multiplying by a scalar. Okay, we're multiplying by 1 over 2 root 5, correct? So it's going to be, 4 over 2 root 5, comma, negative 2 over 2 root 5. So when you reduce the 4 and the 2, you get 1 over 2 root 5. Negative 1 over root 5. Okay? And that is vector U.
Shouldn't you get 2 over 2 root 5?
Oh, sorry. 2 over root 5. Okay? Okay, now let's see what we've created. All right? Let's just take a look. So remember, the first vector was 4 comma negative 2. Okay. All right, let me show you. So the first vector is 4 comma negative 2. And for the unit vector, we got that it's 2 over root 5, negative 1 over root 5. Okay? Now, okay. So, okay, here, what I'm going to do is I'm going to draw vector V for negative 2. So if I start from here, I go 1, 2, 3, 4 over and 2 down. Yes? Now, let me draw on top of this vector U. Okay, vector U has components 2 over root 5, negative 1 over root 5. Okay, I don't know how much 2 over root 5 is. How much is it in decimal? Can somebody tell me how much that is in decimal? Oh. How much?
4.5.
How can that make any sense?
I got 0.89.
Oh, I was so close.
Okay, so how did you do that?
Oh, I multiplied it.
Because,
I don't know.
okay.
You can make it 4 and then divide.
6.9.
So this is, so root 5 is 2.1, and if you divide 2 by 2.1, you get about 0.9. And then this one is, negative 1 over root 5. It's half the amount, right? So it's like negative 0.45-ish. Yeah. Okay? So let's draw that now. So U is about 0.89 and negative 0.45. Okay? So from here, from the origin, I'm going to go to the right 0.89 units, okay, a little shorter than a full one. And then I'm going to go down about 0.45, so about a half. And look, when I do that, okay, it's exactly on top of that other vector. Okay? So it has the exact same direction, but it's got a magnitude of 1. Okay? And often, students have trouble believing that this one has a magnitude of 1. Well, let's see. U, right, it's 2 over root 5, negative 1 over root 5. Let's see what the magnitude is. It's the square root of the first one squared, right? So what would that be? 4 over 5. Plus the second one squared. 1 over 5. Well, what is that?
Oh, 5 over 5, which is 1.
Which is 1.
That's great.
Isn't that cool? Right? Same direction, magnitude of 1. Okay? All right, so going back here, okay, that little unit vector, right, does have a magnitude of 1. In fact, if I like just, okay, so where was it? It was like 0.89 over. It was 0.89 over and like 1 down, right? So that one does have a magnitude of 1, right? But now, if I were to take a vector, okay, that has a magnitude of 1, a unit vector, magnitude of 1, if it was purely horizontal, right? So if I had, or if it was purely vertical, so if I had a unit vector in the same direction as the x-axis and the y-axis, okay, those are special VIP unit vectors, okay? So you can have a unit vector pointing in any direction, but those two special vectors that point in the positive x direction and the positive y direction, those are the two VIP unit vectors, and they have their own symbol. They are given the symbol I and J, but in the books they're bold like that, but when we write them, it's, you know, it's italicized I with a hat on top. That's a caret. We call it a hat. So this is called I hat and J hat. These are everybody's favorite unit vectors, okay? Horizontal and vertical. So in component form, I is 1 comma 0, 1 unit in the horizontal, 0 in the vertical, and then this is 0 comma 1, okay? I hat and J hat. Together, a couple of I hats and J hats can combine and they can create any old vector you would like. So for example, if I were to take 1, 2, 3 I hats and 1, 2, 3, 4 J hats, right? Imagine I put the J hats here, 1, 2, 3, 4. They will combine to create this vector V, okay? So if that vector V has 3 units in the x component and 4 in the y component, how do we write vector V in component form? It's what comma what? Right, which, and how many do we have right now? 3 comma 4, right? 3 comma 4. Now, any vector can be written that way, but also it can be written as a linear combination of vectors I and J. So just like I can write V in component form 3 comma 4, I can also write V as 3 I hat plus 4 J hat. Okay? And if that was 3 comma negative 4, it would have been 3 I hat minus 4 J hat. Okay? All right. Now, suppose you have DE as a vector with initial point D, terminal point E. You want to write it as a linear combination of vectors I and J. I suggest first come up with the component form. So DE is 2 plus 3, 5, 6 plus 3, 9, correct? So as a linear combination of I and j, it would be DE is 5I plus 9j. Okay? And that is what